today we will look at some algorithmic applications on planar graphs of the techniques that we are learning. How we can use these techniques to get better algorithms which are designed specifically for planar graphs. And so yesterday, when Shakil was presenting, he gave a diagram of what we want from a solution. So let's say we have an NP-complete problem. Ideally, what we want is that we want a solution for this problem which is correct and which works for all instances and third thing we want is that it is fast. And in our world, what does it mean by fast? Mostly we want things to be polynomial time or reasonably fast. There are different definitions of fast. Now, as we know for NP-complete problems, we cannot expect all of these three things to be achieved together. So usually we sacrifice one of them. For example, when we sacrifice correctness, we get approximation algorithms. I'll explain what approximation algorithms are. Sometimes we go for graph classes. We say, okay, we don't have a solution for all instances. What happens for some instances which are more practical? For example, I'm designing something for the road network with very high chances. Our road network is either planar or has a very low genus. So if I can have an algorithm there, it's good enough for me. And sometimes we say that, okay, I don't want it to be exactly fast. It can be exponential, slightly exponential. And in this exponential also there are some factors of how exponential a problem is. There are some algorithms which have galactic running time. The one that comes from the Courcelle's theorem that Laurent was explaining, 2 to the power 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 k. So we can't expect them to be like, we say that okay, they are polynomials for a fixed k, but people say that n to the power 1000 is much more efficient than for a very small value of k also. So people don't want to choose these kind of algorithms. So what are fast algorithms? And what are moderately fast algorithms? And what are the instances that make us happy, on which we can make compromise? So in this direction, usually two techniques are used. Let's say approximation algorithms. What does it mean by an approximation algorithm? Let's say we have a minimization or maximization problem. For now, to make things simple, because this is not course on approximation algorithms, I'll keep things very simple. So let's say we have a vertex minimization problem. For example, vertex cover or dominating set. So we want a solution for our problem. We have a problem P and an instance, let's call it G. And let's say optimal, so the size of optimal solution for this instance is K. We can't expect our optimal solution to be achieved in polynomial time for all instances. We know that. But we say, okay, we will still be happy if you can give me an approximate solution. So maybe you will give me a new solution, S, which is not optimal, but size of S is bounded by some function of optimal. And sometimes people even bound it by some function of optimal and n. So we want a reasonably good solution. For example, if we are looking at vertex cover, it's very easy to obtain a vertex cover of size vertex cover S whose size is less than or equal to twice the optimal. Okay, so for these kind of problems, we become very happy. But what happens to a problem like dominating set? It can be proved that for general graphs, we cannot hope to get an approximation ratio better than log n. So these kind of problems are called log n hard. So we cannot design an approximation algorithm which has a performance ratio, this approximation ratio, people usually use alpha here, which has an approximation ratio better than log n. So what happens now? What to do now? So maybe to achieve something better, we need to sacrifice not one of these three properties but two. Let's say we come to planar graphs and I say, okay, planar graphs and approximation. can I do something significantly better? And we will be looking at these kind of things today. Similarly, another paradigm that we work on is fixed parameter tractable. Fixed parameter tractable, we have been looking at that for not writing completely, algorithms. What happens here is that we have an input instance G and a parameter K as an input. And we want an algorithm with the running time f of k into n to the power over 1, which is like polynomial in n, but maybe exponential in k. And this also makes us happy. But again, for our example of dominating set, we know that we cannot expect such an algorithm where k is the size of my dominating set. We cannot expect such a solution. This problem is known to be W too hard. So it's not possible to get an FPT algorithm unless some big conjectures fail. Okay, so what do we do now? Maybe here we sacrifice these two things together. We get an FPT algorithm which is specifically designed for planar graphs. Now, in approximation, and why planar graphs are special? Because in approximation algorithms, the gold standard is something called p-task, polynomial time approximation schemes, which says that I want an approximation for any epsilon greater than 0, which is part of my input. Any epsilon greater than 0, which is a part of my input, I want a 1 plus epsilon, or sometimes 1 minus epsilon, depending on whether you have it. I'll be using mostly this. So 1 plus epsilon approximation algorithm with running time, which is a function of n and epsilon. So for example, I'm happy with something like n to the power epsilon, or n to the power f of epsilon running time. But observe that you can get a solution which is very, 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 very close to your optimal solution, because you can modify this to the 0.00001 depending on the running time you are about to sacrifice. And here, what you want is that we have seen that f of k can be galactic. So there are many impractical algorithms that we achieve. But the gold standard here is sub-exponential algorithms. What are sub-exponential algorithms? A function f of k is sub-exponential in k if it is of the form 2 to the power little o of k. This is little o. So, for example, 2 to the power order big O, k over log k. And mostly, the thing that we like the most is something like 2 to the power order square root of k. If we can get an algorithm like this, we become even happier. Because even for large instances, for example, practically, even if k goes to something like 200, 300, this is still manageable. But for 2 to the power order k becomes unmanageable for 80. You cannot solve it anymore. So this is the gold standard, and what we will look at today is that for planar graphs, we can achieve both of these things for most practical problems. And for this, we will be using the framework mainly that has been developed till now, with very few things that I will be telling today. With this motivation, let's start. Are you excited? Yeah, pen.
It's that green color on the green color duster it has.
So, today, let this denote a k by k grid, and let G of k be class of graphs having treewidth less than equal. Okay.
GK.
Sorry, it's a mistake. I'll be using k for my parameters today. So k for my natural parameter. So that's why I want to use t if it's a mistake. And this is also t. Sorry. So last time we saw a grid excluded theorem, grid exclusion main theorem, which says that if the treewidth, I have a graph G such that treewidth of my graph G is equal to sum f of P, then G contains P as a minor. This we saw last time. And for general graphs, I guess it was P to the power 9. Yeah. For general graphs, it was this f of P was P to the power 9. But when we are restricted to planar graphs, this theorem can be improved significantly. And now what we have is for now what we have for planar graphs, left GPA planar graph, then if treewidth of G is greater than or equal to 9 by 2 P, then G contains P as a. So you see, this improves a lot. This becomes linear. So, well, this is very interesting. Like you can get such a nice bound, and we will be using this particular result almost exclusively to obtain our results. So I should write it here that if my graph G is in G of T by 2, then G contains as a minor.
This graph class is planar, right?
Yes. Sorry. Intersection with, thank you, with planar graphs. And from now on, all the graphs that I will be using are planar. So if I forget to say explicitly, please assume. Okay. Also, such a tree decomposition, also this theorem is strong in the sense that when you are given G as input, then in n squared time, either you give a tree decomposition of treewidth 9 by 2t, or you give a minor model of this grid. What is a minor model? You will give this grid somewhere hidden in the graph. There may be more edges, but you will get a minor model of your grid in this graph of size t by t. So this you can do in n squared time quite fast. So things are nice as of now. So I'll remove it. Now, as a corollary of this statement, we can say that although our planar graphs, we have seen already that planar graphs are the actual obstructions for high treewidth. So if a graph has high treewidth, it has a planar graph somewhere hidden as a, it has a large grid hidden as a minor. And what we will show today is that let G is contained in a planar graph, then treewidth of G is equal to order of square root of n, where n is the number of vertices of my graph. And this is a very simple result. If you want to think for a moment, knowing this, I can give you 1 minute. So let's assume that you have this result. Can you think this is?
Yeah, so this is the maximum width in a plane graph.
Yes.
That's given by the grid structure.
Yes.
That is t square number of vertices and the tree width is t.
Yes. So, for example, if your tree width of your graph, so if you have a planar graph, minor of a graph cannot have more vertices than its actual graph. So if a graph has tree width, let's say t, then it contains, if your graph has tree width 9 by, if your graph has tree width 9 by 2 square root of n plus 1, then it contains a minor of size n plus 1, which is bigger than your graph. Because if you have a grid, T by T grid, it contains T square vertices. So if you have such a, if you have this much tree width, you have a grid minor of size square root of n plus 1 into square root of n plus 1, which contains n plus 1 vertices, which is not possible. So for every planar graph, we know that the tree width is at most square root of n. So therefore, we saw earlier in Thomas' lectures that we can solve many problems in 2 to the power tree width time over general graphs. So, for example, vertex curve you can solve in any case, but dominating set and independent set you can solve in time 2 to the power tree width into only in n time. Both of these problems you can solve in this much time.
Big O of 2.
So, big O. You can solve in this much time both of these problems. So if you can solve in this much time, you can get a square root of n tree width of a planar graph in n squared time. So what you do, you take your planar graph, get a tree decomposition of order square root of n, and once you get such a decomposition, tree width decomposition, you solve this problem, and hence you end up solving both of these NP-high problems on planar graphs in 2 to the power order square root of n time. Which is nice because you want sub-exponential algorithms. But n may be large, we are still not happy. Like for most problems, many problems, you can get such algorithms, 2 to the power square root of n. But they don't make us happy because they are not FPT algorithms. We want something more. How to achieve that? We will do that. So, for planar graphs, these kind of approaches that I am using are called win-win approaches. What are these approaches? Let's take as an example a problem called cycle packing. It has an input G, K, and my G is now a planar graph for now. What it asks is that does there exist K vertex disjoint cycles in G? Vertex disjoint cycles means there are K cycles such that none of them intersect at vertices. So the question is of the cycle packing is that does there exist K vertex disjoint cycles in G? This is a difficult problem. But now let's look at what we can do for planar graphs. First, I would like to make an observation. Let's say you have a T by T grid. Let's say you have T by T grid. This is your input. We can divide this into order T square many vertex disjoint cycles. every t by t grid has order t square many vertex disjoint cycles. There are many other vertex disjoint cycles also if you want to find, but this is one way to get t square vertex disjoint cycles. Now, let's say you are given a graph G, and planar or otherwise, but for now let's say we have a planar graph G, and this graph G admits a grid minor of size, let's say 10 times square root of k into 10 times square root of k. So there is a grid minor, I have a graph G, and G contains this as a grid minor. So almost how many vertex disjoint cycles will it contain? We know that it will contain strictly more than k vertex disjoint cycles. Okay? We know that this will contain strictly more than k vertex disjoint cycles. Now, I am given a planar graph G as an input. And the question is, does my graph contain k vertex disjoint cycles? What I do is that I look at whether my graph has treewidth greater than equal to 45 less than equal to 45 times square root of k or not. I give my graph, I have an algorithm which given a planar graph either gives me a tree decomposition of size 9 by 2t, either gives me a tree decomposition of width 9 by 2t, or gives me this as a minor, and t is given as an input. Okay, I give instead of t, let's say I give 10 times square root of k, or you can give any of these two things as input, 9 by 2t or this. For the sake of convenience, for now, let's assume you give this value as input. So you say to your algorithm that give me a width decomposition of this size, where t is 10 times square root of k, which is 45 times square root of k. You ask your graph, give me a tree decomposition of this width. Either my graph in n square time will give me a tree decomposition of this width, or it will give me this grid minor. This is the property of my algorithm. Either it will give me this, either it will give me a tree decomposition of this size, or it will give me this as a grid minor. Now, why is this situation called a win-win situation? If I get this as a minor, I immediately say, yes, there exist k vertex disjoint cycles. It's easy. Let's say we do not get this. I forgot to mention one thing, but I'll say after I complete my argument. Either it will give me this as a minor, I say yes, there exist vertex disjoint cycles, or it will give me a width with this tree decomposition. And I know, maybe you don't as of now, but we know as scientists, we know that cycle packing can be solved in 2 to the power order of treewidth into only n time for general graphs. So what I do is I plug in this. So I solve my problem in 2 to the power order square root of k into only n time. This is what we wanted. If I obtain the grid minor, I give an order 1 reply, yes, and I stop. If I don't get this, I have to check. Maybe there is something which is hidden without this grid minor. I have to still check. But I can do that check in this time, which is a very good running time. Sub-exponential algorithm parameterized by k and polynomial linearity. If my n is small, if my k is small, this is a very good algorithm. Okay. Now, this is one example we looked at. Let's look at one more example, which is a bit easier to analyze. Let's take vertex cover. We use some properties here that we will formalize once we will look at vertex cover.
cycle separators help you somewhere to solve the problem approximately?
You can do that as well.
So find the cycle separator and dividing by the technique into the number of constant cycles. Does that help?
Of course, yes. But what help do you want? You want to get an approximate solution in polynomial time? Yes, it helps. We will be looking at that as well towards the end. Now let's say we want to find planar vertex cover. We want to solve planar vertex cover. We are given as input a planar graph G and a parameter K. And we are asked whether they exist. And we are asked whether G contains a vertex cover of size at most K. Again?
Can you define vertex cover?
Yes. Thank you. Okay. S is intersection E is equal to yes. So a set S is a vertex cover of my graph if for every edge there is at least one vertex in S. At least one point of every edge should be in S. So this is called my vertex cover. This is a classical problem, and it's a very nice problem in the sense that it gives a two approximation for general graphs, polynomial time approximation for general graphs, and it has very nice running times. It also admits a 2 to the power order k algorithm. In fact, much lesser than 2 to the power order k algorithms also for general graphs.
So the notation for E should be changed because S is a set of vertices and you are making intersection with E.
Yes, so let's denote every edge E as a set of vertices UV.
Yeah, it's fine.
Yes.
And what is planar vertex cover?
Planar vertex cover is when my input graph G is restricted to be planar. You want to find a vertex cover of a planar graph. Okay, immediate observation. I have a T by T grid. Roughly, how much do you think should be the vertex cover of this graph?
T by 2. T by 2.
T by 2 is fine.
T by 2. Order of T square.
T square by 4.
Yes, so it's almost T square. Order of T square. We are more interested in order now. So it's order T square. So for example, you need these kind of vertices. This and this. So you need all of these vertices. So in every such block, you need a vertex. And hence you need many vertices, which are order T square many vertices. Okay. Now, the thing that we did not observe in the previous, I did not mention explicitly and we did not observe, was for this kind of problem to work, one particular property that we need, I said, okay, if I find a grid minor, then I find vertex disjoint cycles. how are we confident that when I did edge deletion, vertex deletions and edge contractions, when I went from G to my grid minor, some of my cycles were not created extra. It will be very easy to see here. So the point is, if my graph G, this property, what I want to say is that for these kind of techniques to work, my problem should be closed under minor, undertaking minors. And what does it mean formally? It means that if my G has a vertex cover of size k, then every graph H, which is a minor of G, should have a vertex cover of size less than equal to k. So if I take a graph, I take its minor, its vertex cover should not increase. And it's a very easy exercise if you think about it. What we do, we either delete vertices, then we delete a lot of edges, so we have less things to cover. Or we delete edges, and again we have less things to cover. And similarly, tomorrow we will be learning about minors more, and then it will become even clearer that even doing edge contractions does not increase my vertex cover. So that's why when I say that I have this as a minor model, and this has high vertex cover, I know my graph also had high vertex cover. And that's why I know when I went from G to a grid minor in the previous problem, and I said that if my minor has vertex disjoint cycles, I can find these many vertex disjoint cycles in the bigger graph as well. If you think about it, these are not very difficult to see. Okay, so now we have two properties as of now. One is that if I have this minor, then my solution is equal to order of t square. My solution requires t square vertices. Second, my solution contains almost t square vertices. Okay. Second condition is that my problem P, I should write something else. My problem Q is closed under minors, undertaking minors. So these two situations are true. Okay.
So first is also for any problem.
No. For the problems that we are looking at, these two. No, this is not true for all problems.
So vertex cover and
And the other one was the one we looked before it. Cycle packing, and I am trying to see what properties, when we pin down, these are the properties that I am pinning down. And once I pin down these properties, I should be able to get something nice. So I did something for the first question, I did something for the second question, and now I am trying to find the patterns so that we can apply the same technique for your favorite problem.
So cycle packing is it minor closed or not?
Sorry?
Cycle packing.
It is minor closed. It was minor closed. That's the prerequisite. Yeah. It's also not very difficult to see. I'll put all these questions in tomorrow's after Sharmik's, when Sharmik will present his lecture. After that, in the tutorials of the Sharmik, I'll put these questions because they will be much easier to see and prove them. But I don't think they should be difficult. And the third question is, so whenever I want to solve such a question, I should ask myself some questions. First, in this grid size, what should be my solution? In such a grid size, what should be my solution? Grid of size t. Second, is my problem closed undertaking minors? And third question that I ask is, how fast can I solve in graphs of treewidth t? So as of now, what I ideally want is that I should be able to solve them in 2 to the power only log. This notation, if I say this k, it will mean order of k log to the power ck. So sometimes we are not worried about polylog factors. So I want is ideally this should be running in this running time into poly of n. And then our framework will be applied. So let's see omega of t square, and my problem is closed undertaking minus, and for vertex cover we know this already, that we can solve this problem in 2 to the power treewidth into n order treewidth into n time, linear in n and order treewidth in this. Okay, so again I do the same thing. I give for some constant c, I ask my planar graph, I have a planar graph G on which I want to find, I have a planar graph G on which I want to find whether this contains a vertex or size k or not. I ask, does G admit a tree decomposition of size, let's say constant times k? This constant can be fixed, it's not very difficult. I ask, let's say this, even if this constant is like 20, it's sufficient for us, or 100, just for the sake of it. So I ask, does my graph admit a tree decomposition, square root of k? Let's say 100 square root of k. I ask whether my graph admits a tree decomposition of this size. Either it will give me a tree decomposition, or it will give me a grid marker of size order square root of k. If this happens, I am happy, because I know an algorithm that runs in 2 to the power order treewidth time, which means I can solve my problem in 2 to the power order of square root of k into n, linear in n and very small in k. And if this does not happen, I get such a grid as a minor, I immediately say no, because you cannot have, x cover is much larger. So the answer to my question is directly no. I say no, it does not admit a vertex cover. So it's a win situation. I know the answer immediately. And the other win situation is I get a small treewidth, which I know how to handle. So we had, let's go again, we have 3 properties. One, I want my solution to be of size of a or a grid of t. I want my solution to be large or small depending on how I want to give the answer immediately. This should be a good bound. This should be of the order t square. The second condition is that my question is closed undertaking minus. And the third thing is how fast I can solve. If I can solve in 2 to the power treewidth log treewidth, or 2 to the power treewidth some polylog of treewidth, we can pitch in and we get a sub-exponential algorithm immediately. So this is a direct framework. You can apply it to any problem you want. Let's look at some examples. Let's look at some more fast examples, and then I'll come to where I want to be. So let's go longest path. So for longest path, the input is a graph G. For us, it's a planar graph G, and a parameter k. And what we ask is that does this graph contain a path of length at least k? This problem isn't hard. Shortest path is easy, but this is difficult. Because if you want to see, if you put k equal to n, you get Hamiltonian path. And Hamiltonian path is hard. So this is one of the most well-studied problems in parameterized complexity. It gave a lot of great insights and tools to handle other problems as well. So the question is, does G contain a path of length greater than equal to k? And the way we have longest path, we have longest cycle as well. And input is same, and the question just changes. Does we have a cycle of length at least k? These two are very important problems in graph theory and graph algorithms. So let's try to fix these problems in our framework. First question: if we have a grid of size t, what is the longest path that we have? Order of t square, because you can go snake-like. Similarly, what is the longest cycle we have? T square. You miss one or two vertices and you can cover almost everything. So you can go like this. And depending on the levels, whether they are odd or even, you can always cover most of the vertices. So here we check. Is this closed under taking minors? So it means if my minor, if my graph G, I get a minor H. If H has a path of length K, does G has a path of length K? So what are we doing? I have a minor model. I'm either putting a lot of vertices in the between, or I am adding more vertices. My path does not get destroyed when I go from my minor to original graph. So this also is checked. And how fast we can solve these problems? Very recently we got to know that we can solve them in 2 to the power treewidth into n time. Earlier they were solvable in 2 to the power order treewidth log treewidth, which would also have been nice for us, but this is much nicer. So we can solve this problem in both of these problems in 2 to the power treewidth into n time. What this gives us? This immediately gives us an algorithm for these problems that runs in 2 to the power square root of k into n time. Do you see why we have this? Because we apply exactly the same framework. We don't even have to change anything. We call the algorithm. Either I get a tree decomposition or I get a minor. If I get a minor, I say yes, I'm happy. If I get a tree decomposition, I compute whether there exists a path. So this is a very powerful tool.
So
But
if I have a minor, so it is by default a yes or no instance for sure.
this is what you want ideally. For those problems, it's a very nice model. So you ask for 3 questions. 1, for a grid of size t, what is the size of your solution? If it is t squared, you are happy. Then you ask if my problem is closed under taking minors. If yes, I'm happy. And the third question is how fast I can solve my problem. But if you remember, let's ask this question again. I started with an example of dominating set. We have looked at this problem, dominating set. I want to find a set of vertices S, such S subset of G, such that for each D and D of G, close neighborhood of D, intersection S, not G. Okay. So this is dominating set, and similarly we have independent set. I'm not writing the definition of independent set because we have looked many times. So, dominating set. I said in the beginning that this problem is not solvable in activity time for general graphs. Also, it does not admit nice approximation algorithms. Now, we want to solve these problems for planar graphs. Let's see if we can solve them for planar graphs using our framework or not. And similarly, independent set. Independent set is also not FPT, and it also does not admit nice approximation algorithms. Both of these problems are very difficult. Canonical problems in some sense. Okay, so let's ask our 3 questions one by one. First question, what is our solution size on a grid of a dominating set? I don't want exact number, I just want an order. Order of t squared. Everybody is convinced? Third question, how fast I can solve these problems on graph of treewidth t? The first example we saw in the first class was independent set. And we solved independent set in 2 to the power order treewidth time. So both of these problems can be solved in 2 to the power order treewidth into n to the power order 1 time. I'm not sure if you can do it in linear time. But yes, they can be solved in 2 to the power treewidth into n to the power order 1 time. So we check box number 1 and 3. How about box number 2? How about property number 2? Can we attack this? Is this problem closed under taking minors? independent set size increases when you take minor?
Yes, if you delete all the edges.
Yes. It's not closed under edge deletion. Right. Independent set is not closed under edge deletions.
But independent set is a maximization problem, the other is minimization. Does it make a difference?
It makes a difference, but what I mean is,
What do you mean by closed? Is it same for both? For both of them?
yes, just a moment, I'll write it down. And what about dominating set?
You can't say from a lower bound, right? Dominating set also doesn't exist of less than k.
So, for dominating set, what will be closed under taking minor means? It means if, so the definition is a little bit like approximation, so it changes whether it's a maximization or minimization. But for what means to be closed under taking minor for independent for dominating set is if G contains a dominating set of size K, then H, which is a minor of G, contains a dominating set of size less than equal to K. Is this statement true?
If there exists a vertex in the dominating set which dominates a lot of vertices,
Yes.
and we remove that vertex.
Yes. So for example, you have a dominating vertex. You take a grid, very large grid, you remove this vertex, which is dominating all of the grid, and you don't have this closed under monotonicity property anymore. This property fails. To check for independent set, what we will check is that if that's why it's a minimization problem. When we take minors, it should decrease. So vertex over is closed under taking minors because if G has a vertex over of size at most k, then H has a vertex over of size at most k. And for the longest path, it was the other way around. If H has a longest path of length at least k, then G has a longest path of length at least k. This definition is similar to the definition of approximation algorithms. Okay, so this problem is not closed under taking minors. So our this thing that I was building up fails for the problem that I wanted to work it for. And many other problems, we can have similarly many other problems for which it will fail. Okay, yeah, let's be quick. Okay, so this will fail, this is the point, this will fail. But we want it to work, and we want it to work desperately. So what do? We need to come up with a new machinery. And that machinery has to be a bit more general, which covers more problems that are covered already. And for that particular thing, some people came together and they came up with the framework of pi-dimensionality. And that we will be looking at now.
Could you please write down the name of the topic to this topic? What you're discussing? I'll maybe start learning this.
Yes, I'll write it down. The one that we will be looking at, the one that we have been looking till now, I'll write it down. Yeah, I should have. Because it didn't start in yet, it will start now. So, if let's say we want to do minimal changes to our framework, we want our framework to be similar, we want to do changes but minimal. For dominating set, 1 and 3 work. What we want? We want our property 2 to change slightly. We want to change this property of taking minors to such a manner such that dominating set and independent set and some other problems fit, which is more general than this particular problem. For this particular thing, observe that dominating set fails when we are taking minors is when we delete vertices. when we were looking for closed under minus. And the other thing, what is the name? Independent set fails when we are deleting edges. So, but what if we only allow edge contractions? Let's say we allow only edge contractions. So we have a graph G. We get a graph H from G only allowing edge contractions. We have G, we do some edge contractions, we achieve H. And now it's not very difficult to see that our problem dominating set is closed under this operation. Okay? Our problem is closed under this operation. Okay. No. In any graph, if you have a dominating set of size k, then you contract edges. If a vertex was dominating some vertices, it will still be dominating all those vertices. It's not very difficult. Let's not go there. It will confuse more. Simple. You only allow edge contractions. We know the operation of edge contractions. I have an edge U, V. You have some neighbors. We have some neighbors, some common neighbors. What I do when I contract this edge, I make a new vertex. And everything that was in the neighborhood, I make it neighbor of this new vertex. So when I contract U and V, I make a new vertex. I delete U. Wait. Yeah, delete U, delete V, add a new vertex. Let's call it W for now, and add edges U X. W X if X is in neighborhood of M of U, and F. So what I do when I contract an edge, I delete. When I contract an edge UV, I delete U from graph, I delete V from graph, but I add a vertex W. And I make W adjacent to every vertex which was adjacent to one of them. So if I keep doing this, whatever my dominating set was, those vertices are contracted to some vertices and they still dominate the whole graph. So this dominates the whole graph. This is closed undertaking. Vertex contractions, edge contractions, and similarly, it can be an exercise that independent set is also closed under edge contractions. This we have seen. Okay. Now, but if I contract my edges, if I only contract my edges, maybe it's not possible to reach to such a structure. What we want now, we want to replace it also slightly. So, people came up with a structure which they call, what do they call this symbol?
Mu.
Tau, mu? Okay, mu of t, which is a grid, almost a grid, with some additional edges. But additionally, you have these diagonal edges. Additionally, we have something like this vertex is connected to all of the boundaries. This is also a planar graph, and let's think that it's connected to everything. It's not very difficult to see. Okay. Now the interesting part is, if my graph, this is the most important result which was true. So remember this symbol. I'll write it.
So only one corner is adjacent to all.
Yes.
other corners are not.
No, only one is adjacent.
And also the diagonals are like not symmetric. These diagonals are not there, right? These diagonals.
No, only one diagonal. Only one diagonal because it needs to be planar.
Okay, so can I do like one is like this, one is like this? Is that allowed?
No.
Okay, this is the exact structure.
This is the exact structure. So maybe we can do, but I don't know.
Is this square root only?
This is a square grid only. This is T. This is okay. Sorry. I should have said this. This is T. This is T, and this is T. From here it comes T. So let's define this structure. Let's name this structure also.
Original graph is grid.
Original graph is grid.
This
There are some
grid we
additional
are
lines.
constructing.
Now, this will again be your assignment question in your tutorial, that if you have a grid in your graph as a marker of size, just a moment. If you have a grid in your graph, if you have a grid marker on your graph of size 2t by 2t, then you can contract edges of this grid. So, for example, this will go to be an edge. This will be an exercise. It will be much better to understand then. That if you have a grid minor of size 2t by 2t, you can obtain this structure of size t by t. So you go from 2t by 2t to t by t by only contracting edges. And not only you need a grid, if it would have been a grid minor, still it would be possible. So using this, it's not a very complicated proof, it's a very simple proof. We'll try on the tutorial, and if it will be difficult, I'll give it to you. So, but the main part is you get a new kind of grid exclusion theorem. And this grid exclusion theorem says that if you have a graph, planar graph G, and you are given some input T, then either or your graph has treewidth 90 plus 5, a little bit more. It was 90 by 2 before, but now it's 90 plus 5, a little bit more, but order doesn't change. Or either your graph, you get a tree decomposition of this width. There exists an algorithm which runs in time order n square. For a planar graph G and input T, it either gives you a tree width of decomposition this, or it gives you this as an edge contraction. Either you obtain this tree width, or you obtain this as a decomposition, edge contraction.
So G is a planar graph?
G is a planar graph. This is only true for planar graphs. No, it's not only true, sorry, but it's true for planar, not true for general. It's true for some other minor free graphs as well. So, okay. Is this clear? Now, starting from here, most of you can maybe see that we already have an algorithm for dominating set and independent set, because what I do, I simply increase my constraints. If by any chance I get this graph, if I get this graph, what is the dominating set of this graph?
You are adding them, so we have multi-edge here? From that bottom right corner, we have multi-edge or I multi-edge?
To where?
To this table, left table.
Oh, sorry, yeah. No multi-edges. Although they won't hurt, but no multi-edges. You cannot get you are never guaranteed to get a multi-edge as a contraction. Maybe, yeah. So there is no, it was not a multi-edge, it was a mistake.
Amanda, can you perhaps write a little bit more, because Zin is
taking photos, but can you write treewidth at most 90 plus 5, these things?
Also, then I have notes.
Yes,
I
yes,
just
fine.
prepared, so I'll give them also to you.
Yes, yes. That is helpful.
Now, again, I have this graph. It's not very difficult to see that all the properties that we were looking at as of now follow here as well. This vertex is a bit powerful because it covers the whole of the boundary. So, and it covers many things. But the moment you leave the outermost layer out, it becomes almost a grid. The vertices are not so powerful. So all the things still remain. So dominating set of this graph is still t squared. When this is t, it's still t squared. Now my dominating set and independent set are close undertaking edge contractions. Let's remove this. Let's only write contractions, not edge contractions for now. Contractions. And how fast my algorithm can solve, this stays the same. So immediately we jump to a larger class of problems that we can solve. And the problems that we can solve using this are yes, for feedback vertex set, I did not mention. If you want, you can check that feedback vertex set also follows this property. Feedback vertex set in a graph is that G and K, this is our standard thing for some time. A set S is feedback vertex set if for every cycle, if, okay, easier, sorry, if G minus S is a 4S. So a feedback vertex set is a set of vertices which you remove, then your graph becomes acyclic. So, if you look at feedback vertex set, again, for this graph, at least t square, it's closed undertaking edge contractions. If you close, if your whole graph has some feedback vertex set, you contract edges, your cycles can only decrease, they can never increase, and the vertex still remains in the same cycles. And you can solve it again into the power of treewidth, I guess, treewidth, whatever, but it can also be solved in sub-exponential time. So the problems that you can solve in sub-exponential time are, other than the ones that I already mentioned, feedback vertex set, induced matching. Induced matching is difficult, unlike its counterpart nodal matching, and cycle packing, longest path, longest cycle. So this also has applications in approximation algorithms, which we will come to later. First, I'll define something called local treewidth. We'll do the approximation from that point of view, and then we'll come to this.
So what I was saying, these problems, sir, how can we, yeah, you were saying something, these problems, sir?
Bidimensional, and all of them fit this framework, and hence all of them admit a sub-exponential algorithm, 2 to the power little of k into n to the power 4 to the 1. Mostly they admit 2 to the power order square root of k, possibly some log k, and n to the power 4 to the 1, which is a nice running time.
What is bidimensionality mean?
Bidimensional in the sense that either you get this or this. Win-win situation. Either you have immediate yes or no answer. So this is the application. You apply your framework, either immediately yes or no, you don't have to compute anything, And in fact, most of the algorithms which are sub-exponential uses this framework in some manner. Things can change a little, but mostly they are using this framework. There are some, although there are some results which are complicated, but mostly this.
So problem is b-dimensional if it admits these three properties.
Yes.
That's what you're saying.
Yes. And I didn't, because to define bidimensionality, it requires too many definitions.
It's more general than that.
It's way more general, and it's not only defined for planar graphs, it's defined for -3 graphs, apex minor graphs, apex-3 graphs, and also graphs on bounded genus. It's more complicated than this, but these kind of problems are called, for planar graphs, they are called P-square bidimensional. If it admits these three properties. Yes, I should have said this. Some places they call it this, but not the original paper. So, we at least looked at, and I guess you might have realized that treewidth is at the center of all this. Although we are going into planarity, but treewidth is at the center. Now, we will be looking at a technique which is called shifting technique or Baker's technique. So this was given by Baker, Professor Baker, and it was originally given for approximation algorithms, and it used something slightly different than treewidth, which was also a width decomposition of planar graphs, but it can be very easily adapted to treewidth and R framework, and we'll see. First we'll see, should we have a break or?
Yes.
Yeah, so let's have a break of 10 minutes and we'll soon.
5 minutes.
10 minutes. which is also very interesting in its own right. It says that although planar graphs have unbounded treewidth, but if you look locally, they have bounded treewidth. So if you take any planar graph, you take any vertex, and you take a ball of a fixed bounded radius around it, it will have a bounded treewidth. So, in some sense, it says that if you want a larger treewidth, you need to have a very big radius graph. And these, we will today look at how to utilize these piecewise components, each of which will have bounded treewidth, to obtain both FPT as well as approximation algorithms. So, yeah, let us start with this technique, and let's say that we have a planar graph G, and we are given a number R, which is greater than or equal to 0. And let's say G R F V is, okay, first let's define something. Let's say we have a vertex V, and we do a BFS around V. So these are vertices which are neighbors of V, which are at distance at most 1, we call them L1. These are vertices at distance at most 2, L2. And this way, we keep growing our graph, and this is what we will call a ball of radius 3, and you can generalize to any ball of the radius. Now, GV of R is the subgraph of G induced by layers G L0 to LR. L0 is the vertex itself, and you see the layers. So you do a BFS, and you go till levels R. So this is the subgraph of G induced by LR, and so this will be G 3 0. If I take till this level, this is G 3. And the first observation that we have here is that treewidth of this particular graph is bounded. The first one is it okay? So, first result is that follows from our previous results is that treewidth of G R E is less than equal to 18R plus 30. So first we will show that they have bounded treewidth. How do we show that? We are talking about planar graphs.
So S0, L1 are just neighbors, right? 0 is neighbor, first neighbor, second neighbor.
Yes. So this is just a BFS. Instead of showing it as a BFS tree, I'm sure.
Maybe not everybody knows BFS.
Oh, so I from B. Similarly, when I explode my graph in this manner, so the vertices, let's say that there are many levels. This is L2, and they never intersect, by the way. So let's say this is ith level. Then distance from B to any vertex of Li is exactly like. Okay. Now, what we want to do is that if I take this graph from here to Lr, and I take all the vertices and I induce this graph as a subgraph of my graph G, then I am claiming that treewidth of my graph is bounded by this particular number. And let's take that is given as an input. Let's say that this is greater than or equal to 18R plus 14. Okay. Then, if my treewidth is greater than or equal to this, I will find a minor in this this as a contraction, where T is equal to 18R plus 14 minus 5 over 9, which is equal to 2R plus 1. So what I will find is this thing. Yeah, is this clear? Why? Because if I have my treewidth is greater than or equal to 9t plus 5, then my graph contains this as a contraction. So, if my treewidth is greater than or equal to this, my graph will contain minus 5 divided by 9, or this as a contraction. So, if my treewidth is this, I have this as a contraction, and if I have this as a contraction, I can, let's say that you have grid. This is 2R. This is not grid, but this is connected to everything. And let's say we have this. Now it's not very difficult to see that, like it requires a little bit of exercise, but it's not very difficult to see that in this, when we get this as a contraction, why we need as a contraction first of all? Why can't we simply do with minus? Because when we have contracted, our original vertex V is contracted to some vertex here. Let's say this vertex. It has been contracted to some vertex. So that vertex V still exists. Now, by definition of this graph, the existence of this graph, every vertex V should be at distance at most R. But if we have 2R plus 1 by 2R1 plus this grid kind of structure, then it's not difficult to see that there will be at least one vertex which is at distance at least R plus 1, which is not possible. Because if this is the vertex, the center vertex is far. For any vertex, there exists at least one vertex which is far, at distance at least R plus 1, which is not allowed by definition, because to the vertex where V is contracted to, every vertex is at distance at most R, and the longer and the shortest distance is closed under taking contractions. Your shortest distance cannot increase. But here it increased, which is a contradiction. It implies that treewidth of my graph is locally bounded. So if I go to R levels, my treewidth cannot be more than 18R plus 13.
So why we taken that 2R plus 1? Just all the grid size.
It's sold to this.
2R plus 1. From that, like how we are using that thing? TW.
I'm saying if my tree width is greater than this, okay? If my tree width is greater than this, then I should contain something as a contraction. What is this value? I'm doing back calculation. It's if it was 90 plus 5, it was t.
So this comes from a theorem, right?
Yes.
I think that's unclear.
This is a theorem I have
It's a theorem by some people.
This is a theorem that if my tree width is more than 18r plus 4, if my tree width is more than 90 plus 5, then it contains this graph as a contraction. Now, you simply fix their values. If this is 18r plus 14, it will solve to 2r plus 1. Your graph will have, if your tree width is at least this, your graph will have this as a contraction. And if your graph has this as a contraction, your vertex is not deleted because it is contracted. It has been contracted to something, and distance does not increase while taking contraction, and it increased. It implies our assumption was wrong, and hence our tree width is bounded. So, although the tree width is unbounded, but if you look locally, you can take care of things. And this is very, very important for planar graphs, this technique, and we will very soon see why.
So diameter is t, right? Diameter of ut is t. The diameter of ut is t, right? That's why here diameter is 2r plus 1, so you cannot reach here.
Yeah, it's difficult to prove that it's t, but it's of order t. If I take 2r plus 1,
Diameter is
2r plus 1, then the diameter is at least r plus 1. For any vertex, there exists a vertex which is at distance r plus 1. Diameter is the longest path. But we are saying for any vertex we choose, there exists a vertex which is at distance at least r plus 1. And it's just a plain simple exercise. I'll put this also in the exercises. Okay. Now, but this I just wanted to show you that we can obtain using our knowledge. But this is not a good bound. The good bound is that if your graph can, for this particular thing, your tree width is less than equal to 3r plus 1. So this is not something we have proved, but this is the best bound. This is more difficult to prove, so that's why we are using it directly. We prove a slightly easier to prove bound. Okay. Now, let me write this also. Now, let's look at one very simple application of it. Let's take a vertex V, arbitrary vertex V, and let's make layers. Okay. Now, what I want to say is that I define something called a graph I through I plus j minus 1, which is nothing but your graph induced by layers Li through Li plus j minus 1. So, this is your V, this is your Li plus 1, and so on, Li plus j minus 1. So your subgraph induced here is called Gi plus j minus 1. Is it clear? Now, we have this includes j layers, and the next that corollary of our result is that treewidth of this thing is also bounded. Treewidth of this graph is less than equal to 3j plus 1. So this means, what this is saying is that not only you have to take the layers which are centered around the circle directly, centered around the vertex directly, but you can go to any layers of the BFS, you pick any layers, and they still have bounded treewidth. The proof is super easy. What is the proof? That you contract all of these layers to one vertex, and then you have the same logic. You contract all of these vertices to one vertex, and all of the things that we did before applies. So this, if I take if I take these two layers, my treewidth is bounded by at most 7. If I take these 3 layers, my treewidth is bounded by at most 10. And I can do this anywhere I want.
But wait, this works because treewidth is stable by contraction. No? I think you have to say this.
Yeah.
Because you're contracting something, you get the tree decomposition of the new graph, right?
No.
No?
The proof was simpler. The proof is simply this, that I contract everything here. Maybe that is a simpler. That
you get a new graph now. You get a new graph.
You get a new graph in this graph, but my treewidth decomposition is only of this part. And in this part, this is simply a vertex. What I do is I contract everything till this layer. Now this is one vertex.
So you have one vertex which sees everything.
Which is?
Which sees the whole first layer, no?
Yes. So you have a vertex which sees whole layer, and it is present in all of them. No, sorry. Which is here, and what is the problem I don't see? Sorry.
You can think of it like you remove 2 strips of the circle.
Yes.
And then the graph induced on between those 2 strips, their treewidth you are trying to bond.
Yes.
So.
Yeah.
I think what he wants to do is he wants to replace all these first layers that he has removed by a single vertex. That single vertex, you make it adjacent to the whole layer number I.
Yes.
That gives you a new graph. Still planar.
Yes.
So now you can apply it to you get by this theorem and tree decomposition of this new graph.
Yes.
From that you have to deduce a tree decomposition of your original
Original graph. Yes.
So you have,
So
requires some explanation.
So this vertex, which is a new vertex, is not in my new graph, but it is in my decomposition. I can replace this with any of the vertex in all the lines. It's not a problem.
Because you have a subgraph. Right?
Yes.
So still, some steps you have to explain, right?
Yeah, I thought because we have been talking about treewidth for so long. Okay.
Can you repeat this? So you are contracting everything from B to the layer I minus 1?
Yes, we contract everything from B to layer I minus 1. And then, including this vertex, I can get a decomposition of my graph of width 3j plus 1. Now, in this decomposition, we just have a vertex extra. You can replace it with any vertex of the graph. Put this vertex in every band.
But you have to say that this graph now has what is the radius of the new graph? You have to use this to get your bound, right?
Which one?
You have a new graph.
Yes.
Where you have this central vertex. What is the radius of this graph? You're bound, right? You have to say that. So the radius is just what? J minus I something.
This,
so
my radius is J.
J.
This
right?
is increased by J.
So the theorem tells you the treewidth of the graph where you have U
is 3j plus 1.
Exactly.
Yes.
So that means the original graph also had treewidth at most 3j.
These vertices, graph induced by these vertices, have treewidth 3j plus 1. This is what I want to say.
Exactly, but you didn't say it. So I'm just saying that to complete the explanation.
Okay.
That's how you have to explain.
This is what I said. Okay, whatever. So is it clear now to everyone what I wanted to say? Okay, so let's move ahead. So the point is, you take any layers here, your treewidth is bounded. Any bounded number of consecutive layers, your treewidth is bounded. Now, what you can do further? What you want to do? Now, what we will do is that we have this layers L0 to something, I don't know what is named. I want to partition my graph into k plus 1 independent sets. Oh, sorry, k plus 1 disjoint subgraphs, which will be S0 through Sk. I want to partition my graph into k plus 1 disjoint subgraphs such that if I take any k of them, maybe I should use G here instead of S. It's easier. So I want to partition my graph into k plus 1 subgraphs G0 through Gk such that if I take any k of these subgraphs, or in other words, if I remove any Gi from G for I in 0 through k, then treewidth of this graph is bounded. Treewidth of G is bounded.
The same G you're taking, the Gi plus J minus 1, or this new G? What is this G now? Any planar graph, or is this G?
G is always a planar graph.
Not that one.
Which one?
Which would be I plus J minus 1.
This is a different way of defining a subgraph. This is a different way of defining a subgraph G1, G2, G3. What I want to do is that I want to partition my graph into k plus 1 disjoint subgraphs, vertex disjoint subgraphs, such that any k of these subgraphs have bounded treewidth. So if I take one of these subgraphs out of my graph, my whole graph has bounded treewidth, bounded by k. And this is a very strong result, that planar graphs are these graphs which have unbounded treewidth, but I can partition any of my planar graph into k plus 1 components, and if I take any k of these components, I have to only leave one of them, and that too of your choice. I partition it, you say that I want to take out this particular component, and now the treewidth of my graph is bounded. And this is what we will be trying to prove today, or trying to see today. This is called Baker's technique. And
G0, G1, G3 are induced.
yes, these are induced subgraphs. All of them are induced subgraphs.
Induced by those layers.
Induced by, these will be induced by some layers. I'll define how to get these layers. So G0 is bounded, is some set of layers. G1 is some set of layers. And G1 is defined by some set of layers. And this way, for each of them, I'll give a set of layers. And then, if you take any of these subgraphs, and you remove just one of them, treewidth of your graph will be bounded. Very simple manner. You have already guessed it, I think. So this is L0. So my G0 will be L0 union L. Just a moment. Just so that you don't make a mistake. So G0 is equal to L0 Lk plus 1 union Lk plus 2k plus 2, 3k plus 3, dash dash dash. G1 is equal to L1 union Lk plus 2 union 2k plus 3 union L 3k plus 4. So what I do is, what I am doing essentially is, I am taking this, I am starting from, first I am starting for G0. What I do, I take the first vertex, my center vertex, then I take my k plus 1, I leave k, k consecutive people, and I take k plus 1, 11k plus 1. Then again I leave k in between. Then I take L2k plus 2. Then I again leave k and take L2k, 3k plus 3. Okay? This is what I am doing. Now, what I do, how do I take graph 1? So these are just my layers mod this particular number, k plus 1. So what I do next, this L1 goes to my G1, then I leave k plus 1, then I leave k and I take the next layer, then I leave k and I take the next layer, and this way. So the formula is the following, that the layers in Sj, Gj will be collection of layers that are of the form A times k plus 1 plus j. This is k plus 1 because there are k plus 1 of these partitions. So A goes from 0 to whatever we need to do.
So this result depends on k. What is the value of k? Should be true for every k?
Yes.
Every k.
It is true for every k.
So the indexing for L is still?
Sorry?
The layer is the indexing for L.
The diameter of the graph. So like the diameter of the graph starting from B. Whatever is the maximum distance of the vertex starting from B. You explore the graph.
More doubt. This boundary that you are doing through BFS, it has a limitation. It will not go infinitely.
Of course.
Yeah.
It's a finite
For
graph.
every k, how we will ensure like this? This will be disjoint.
Disjointness is guaranteed. Because what you are taking is, this is the formula. Gj will be collection of layers which are of the form A times k plus 1 plus j. So, for example, you also can see it in the form of mode. You take any of the layers, you take its mode with k plus 1, and then it will go to that particular. And this is an exclusive formula. It sends one person to one person.
So this should not be, this case should not be the larger than that ball size.
Why it cannot be larger than the
Like
ball?
the ball size, suppose if I am taking BFS and BFS size is going up to R,
Yes.
it's not go beyond R.
Why not? Why can't you go? You can take in whatever you want. It's just that some of these will be empty.
Oh, okay.
But you can take whatever you want.
Okay, that will be.
Some of them will be empty. You also had a question?
Can you explain this part? What are this G0, GK, and
Which one? This one?
last part? Yeah, last one.
This one. Here I am trying to give you a construction how to construct GJ.
Can you show on the picture?
Yes,
Easier.
I showed.
Colors.
So these things we are doing for planar graphs only, or like this is true for the
I am trying to do everything for the planar graph. You can define all of these things for any graph you want, just that the properties will not fall into picture.
So what property this k of the distance of class?
Any k of this graph G minus this, what?
Any k of these subgraphs are such that if you remove one of these subgraphs from your graph will have bounded treewidth
G minus Gi have bounded treewidth.
for every I.
And what is that treewidth of G less than or equal to? Will conclude from this?
No, I was writing that treewidth of G minus Gi is less than equal to 3 times k plus 3. I guess this one maybe because of plus 1 there can be something hiding, but it's this 3k plus 3.
Yes, then?
Sorry, and also there is this I.
Yeah, if this happens, then what?
No, this is what I want to happen. This is in itself a very strong result. This is what I want to happen, to make it happen.
So this will not hold if I will remove 2 or more than 2.
Treewidth is closed undertaking subgraphs. You can reduce after that whatever you want. If your graph has a treewidth at most k, every subgraph has treewidth at most k. So if you remove more, it's even better. But what I'm trying to say is that you don't need to remove more than one. You can partition in such a manner that if you remove even one of them, you are very happy. Your graph may have unbounded treewidth, but you just let me remove 1 by k plus 1 of your graph. And I'll let you choose which of these k plus 1 by k plus 1 you want to remove. Still the treewidth will be compounded. This is what I want to establish.
Even G has unbounded treewidth.
Of course. Then only, yes, G may have unbounded treewidth. So, again, maybe I should make smaller circles, no? Then it will be better. Let's take k equal to 1, 2, 3, 4. Let's take k equals to 3. So this is my G0 color. This is my G1 color. This is my G2 color. And this is my G3 color. My k equals to 3.
Union over
Yes. I guess this should be sufficient. Okay. So my G0 will be this vertex, this layer, and maybe one more outermost layer. Okay. Is it clear? So this is my Z. I write also. This is my 0 level. This is my G0, this is my G1, this is my G2, and this is my G3, and my k equals to 3. Now, look at this formula also. My 0 times 4 plus 0. 1 times 4 plus 1, 5. 2 times 4 plus 1, 9. And 3 times 4 plus 1, 13. So these layers, all of these layers, if you are looking, belong to G0. Okay? Next layers, immediate next layers are G1. Then next layers are G2. And similarly, I go back to Z0 again. G0, G1, G2, Z3. Okay. So this is how my GIs are defined.
So this GJ has union is there or not?
Yes.
Union.
Yes. This has union. So is it clear now for everybody? Now maybe this. Okay. Now let's say that for now, let's say I delete everything from G0. Okay? Or for any line that you want to delete. You delete any color. Let's say you delete blue color. Okay? What is happening? When I delete blue color, this will disconnect my graph because of planarity. Is it clear to all of you that this will disconnect my graph because of planarity? Now when it will disconnect my graph because of planarity, what I will have these 3 layers, then these 3 layers, then these 3 layers. I will have my graph as a disjoint collection of these layers, which are consecutive. Okay? And I have established that, let's say that I am deleting view. I have some graphs like this. And this. Okay? And this. I have subgraphs like this when I delete this particular layer. So I have established here the treewidth of such graphs when I have only 3 layers is what? 3 times k plus 1. Here k is 3, so it's 10. But otherwise, all of them have 3 times k treewidth at most. 3 times k plus 1. And since these graphs are disjoint, all of these subgraphs are disjoint, when I collectively take them, I can merge these 3 decomposition at any place. It doesn't matter, because if I have a disjoint, if I have subgraph, and I have a completely disjoint subgraph, and I take their 3 decompositions, any 3 decomposition, I merge them at a random vertex. I put a random edge. The 3 decomposition is still a 3 decomposition because there is no edge. Vertices are already taken care of. There is no edge across them, so you don't have to take care of everything. And connectivity is already taken care of. So it's still a 3 decomposition. So if you delete any of GI, what you are left with is a collection of k concentric cycles. K concentric cycles. Each of them has bounded treewidth. So if you are allowed to delete any of GI, you can bound the treewidth of the remaining graph. Till here, it's fine. Right?
Here you say 3k plus 1, whereas there you say 3j plus 1.
Because here it was defined in terms of j, and here it is defined in terms of k. These are k layers. Here it was j layers. It doesn't matter. These j and k are just variables.
That was a different problem.
It was for this. And let me do it here so that it's not a problem anymore. Okay.
That was different.
This is different. But I'm using this statement only. Because of this statement, I know that if I take any k consecutive layers here, their treewidth is at most 3k plus 1. And if I delete anything, any color from here, what I am remaining with? K consecutive layers, k consecutive layers, k consecutive layers. Each of them with bounded treewidth, which gives me a bounded treewidth of the whole graph. Okay. Now, let's come to a problem which is a bit difficult, generally. The problem is subgraph isomorphism. And we will solve using this technique. I can remove this part, right?
I know. Take care of the time.
Done?
It's been 2 hours, so I don't know how long
I mean, time is over, right?
How much do you need?
Maybe I'll skip the approximation then. I'll just finish the homomorphism. It is isomorphism, it only takes 1 minute. Approximation, if I have to cover, I require 5-10 more minutes. Let me at least cover isomorphism and then we'll ask.
So treewidth was
3k plus 1. Because we have k consecutive layers, not k plus 1. I am deleting the 1. So that I am just giving an example of a problem so that we at least have some motivation why we studied all this and why this becomes important. Subgraph isomorphism. So here you are given a graph G and a graph H, and what you want to know is that does G contains a subgraph isomorphic to H. And what is isomorphic? Two graphs H1 and H2 are isomorphic to each other if there is a mapping from H1, V of H1 to V of H2 such that, if there is a bijection from H1 to H2 such that if there are two vertices u and v, they have an edge. Fu, Fv is an edge, and their images are also. So you take a graph, you want to find an exact copy of that graph. Now this problem, when you take only treewidth, we don't know if we don't have an algorithm which is of the following form: f to the power treewidth into n to the power order 1. Such an algorithm we don't have. But what we have is that we have an algorithm of the form f of treewidth, size of h, and n to the power order 1. In fact, size of vh, but it doesn't matter for us here. So let's say v of h. Okay. So we have an algorithm of the form f. Let's keep it on the h to keep things simple. So to solve this problem, we have an algorithm that requires time f of treewidth and h and polynomial n. But we want to solve it on planar graphs when both g and h are planar, only as a function of h. We don't want to invoke treewidth. We want an algorithm which is of the form f of treewidth, f of h, because h is usually smaller than g, into n to the power order 1. We want such an algorithm. How do we do this? If let's say we want to find a graph isomorphic to h. Here, let me set k is equal to vertex set of h plus 1. Okay. What did I set k? To be vertex set of h plus 1. Sorry. Let's not take plus 1. Let us do k is equal to vertex set of h. And do a similar subdivision from g0 to gk. We did it. Now, we know that if my subgraph is isomorphic to some other graph, my subgraph is isomorphic here, it can contain at most k vertices. And hence, these k vertices, it will miss at least one of these. So since it has at most k vertices, and I have k plus 1 components, at least one of these components will not be contained. When I get a solution, at least one of these components will be missing. So one of these components do not contain my solution. So what I do, I run an algorithm for I is equal to 0 through k. I take my graph g minus gi. It has bounded treewidth. I find its tree decomposition and solve my problem in f of, since it has bounded treewidth, bounded in what? Vertex set of h. So it was earlier treewidth and size of h. Now, because my treewidth was of the size h, this is simply with running time f of size of h into n to the power order 1. So what did I do? I take my graph, I make my layers as per this graph, I delete my layer one by one because I know my solution does not contain vertex from at least one of these layers because I have k vertices and k plus 1 layers. So I delete that layer, and for all practical purposes, my graph has bounded treewidth. And this is what is called Baker's technique, and it has many other applications. You can apply it to many problems. And this particular problem required this partitioning, so that's why I wanted to present this problem in partitioning. Now there are some approximation algorithms, but the time is up, so maybe tomorrow or later. If somebody is interested, you can ask. Thank you. You have a break, and you can ask me questions.
10 minutes. We start in 10 minutes with the tuning presentations.
Yeah, because they are favored. And at least one of them do not have yes. It's not so difficult from us, but here we have proved that my favorite is of orthogonal.